It seems there was a network issue from my end, so I'll just try to reintroduce myself again. Welcome back again to the week 10 of the problem solving session for the thermodynamics course. And again, we'll be discussing about the entropy and the second law of thermodynamics. We'll continue to discuss about the entropy and the second law of thermodynamics like the previous sessions. To just give a idea of what we'll be doing today. So similar to all our previous sessions that we have conducted, we will briefly go through the topics that were covered by Professor Anand in the lectures. Of course, I'm not dive deep into each and every topic or discuss too much. I will just try to briefly go through them once. If there's any doubt, it can be asked. I will try to clear them up as much as I can. But if there is still any doubt, you can just go back to the lectures. I think there would be something or some way that you will be able to clear your doubts, or else you can put that out in the discussion forum for this course so that we can work upon that. And there are always standard textbooks that can be followed, as I said, Professor Anand. So we can do that. Okay. With that, let us start today's discussion. So in the previous week, I'm sorry. So in the previous week, we formally defined what entropy was. That entropy is defined for a reversible process. Like it does not mean that it is not meaningful for irreversible processes. Of course, it does, but an equation or a proper definition for entropy is clearly defined for a reversible process only, or in terms of a reversible process. So we found out that entropy or a change in entropy in a more correct sense is the ratio of the heat transferred in a reversible process over the temperature at which the heat was transferred. So that's the very definition of entropy. And we see that we also introduced the TS plot in the last lectures, in the last lecture. So previously, before last week's lecture, we have been primarily working on this PV, the pressure volume plots or pressure temperature plots, and we also actually discussed about the temperature entropy plots. But I mentioned time and time again that since we have not formally introduced entropy, then I don't think it would make much sense. But we tried to take the aid of these TS plots to make you understand different thermodynamics processes. But still, since we discussed and formally introduced entropy, we also discussed in the last lecture, we also discussed about the TS plots there. And so for, if I remember properly, it was for Carnot cycle. And so we'll continue to use that in the later part of in today's session, as well as in the later part of this course. And yeah, so we see that for an isentropic process, that is a process where the entropy remains constant, we say that S is equal to constant and the change in entropy is equal to 0. So in a TS plot, if you look into it, the isentropic process, let me just draw it. This is the temperature axis and entropy axis. So the change in entropy can be represented by a vertical line. Okay, either it goes either temperature goes down or temperature goes up in an isentropic manner. Okay, so we saw that for Carnot cycle, we can draw the Carnot cycle in this manner. Okay, a constant temperature expansion, then isentropic expansion, followed by a constant temperature compression, and then an isentropic compression. Okay, so this was, and the heat additions were done in the constant temperature way. Okay, so this was the Carnot cycle in a TS plot. So this we have already discussed, so we will try to continue. Okay, then we also say that a isentropic process can be evidently be also told a reversible adiabatic process, or a adiabatic and reversible process, as discussed here. So So in other sense, if if a process is adiabatic and reversible, we can tell that the process is isentropic, or sorry, yes. Okay, so let us go to, let us proceed further. I think it's clear here till now, so let us proceed a bit further. So here we will discuss about the different types of uh, processes and how they are represented on a PV plot. Okay, so this question was also discussed in the previous sessions as well. That is the slope of a constant pressure and a constant volume process, and how does it vary in a PV plot. Okay, so if there's any remarks, if you know whether about this, you can suggest. Like, of course, it has already been shown here in the TS plot at least that a constant volume process has a higher slope compared to a constant pressure process. Okay, it has been shown here. So of course it is not yet evident, clearly evident till now, like why this matters, but you will see that especially in the case of, say, when we discuss about Otto cycle and diesel cycles, there are processes which are specifically mentioned to be a constant pressure process and a constant volume process, especially in diesel cycle. In that case, the slopes of those processes in the PV and the TS plots, sorry, in the TS plot specifically also matter. That we need to show them clearly, so that like for example, if you do a PV plot and when you draw the constant pressure and the constant volume processes, sorry, in the TS plots, you need to be consistent in the slopes of those processes. Like for a constant volume process, the slope would be higher compared to a constant pressure process. But why there is that? This was actually discussed as one of the example questions in the assignments, but still, just give me 1 second. Since it has been rediscussed by Professor Anand in the lectures of the previous week, I think I would like to go through them once. Okay, so this was the derivation that was taken by Professor Anand. Okay, it was a simple, small derivation. Okay, there's also an elaborate derivation that was taken in the assignment question, considering the partial derivatives. That would be a more robust, I would say, a more robust discussion on that. But I think you may, if you want, you may go back to the assignment solutions that are in the recordings of this course's problem solving session to understand that. Okay, but still, let us just go through them once as discussed by Professor Anand. So I think the screen is visible. Okay. That for an ideal gas, from the thermodynamic property relations that we have discussed in the last lecture, we can write TdS is equal to du plus PdV. Okay, so how it is obtained, I think I will not go through it again, because we have thoroughly discussed this in the last week lectures. So we can, for a constant volume process, that is V equal to C, then the PdV part, specifically the dV part, becomes equal to 0. So you are left with TdS is equal to du. Okay, and similarly we can also, we have the other relation as TdS is equal to dH minus VdP. And for a constant pressure process, we get that dP part becomes equal to 0 since P equals to constant. So we have TdS equal to dH. Okay. Now from the first relation, we got that TdS is equal to du. Then TdS can be written as CVdT. That is, for an ideal gas, the change in the internal energy is written as CVdT. Now, for simplified conditions, we can consider this to be a perfect gas, or a calorie perfect gas, where the specific gas constant at specific heat at constant pressure remains constant. It does not vary with temperature. So in that case, we can write this dt by ds is equal to T by Cv. Okay, so that's one of the conclusion. Okay, given that your CV uh, remains constant, with is a constant. Okay, so we consider as an calorically perfect gas. Okay, we'll see why it is necessary in the later derivations. Okay, and also we can consider the second relation, that is TdS is equal to Th in this equation. Then we can write TdS is equal to Cp dt. Again, the change in the enthalpy for an ideal gas can be represented as Cp times dt. And if we consider again a calorically perfect gas or Cp to be constant, then dt by ds is equal to T by Cp. Okay. Now the catch is that from both of these equations we get the slope in a Ts plot. Okay. So if we consider a Ts plot, let's draw it again. dt by ds represents the slope of a curve. Okay. So there is a particular curve represented in the Ts plot. Okay. Then dt by ds, sorry, dt by ds would essentially represent the slope of that curve. Okay, slope. Okay, so dt by ds represents the slope of a curve in the Ts plot. Now, since we know that Cp is always greater than Cv, that is from the relation that Cp minus Cv equal to R, then Cp is always greater than Cv. So it will imply that if Cv is greater, then for a constant volume process, the slope of the curve of a constant volume process is always greater than the slope of a constant pressure process in the Ts plot. Okay, so that is the conclusion that we get from this discussion. Okay, so I hope it is clear till now. Okay, then we can proceed. So okay, so then in the last week, if I remember clearly, last week and the previous week as well, if I'm not wrong, we discussed about these irreversibilities. Okay, we like in a theoretical way we discussed about how these irreversible processes can generate entropy, and that generation of entropy may affect the efficiency of these systems. Okay, so now we just try to formally look into those irreversibilities. Okay, so while discussing about the steady flow energy equations for say turbines, nozzles, compressors, and all these devices, specific devices that we have looked into while discussing the steady flow energy equation, we looked upon their expression for their say work done or the net heat transfer and all these things. Okay, so but in those cases, I mentioned it in the lectures, but in those cases we clearly stated that we are considering the process to be reversible. That's why we are able to represent the change in the say pressure or the entire process or the cycle through solid lines in the PV diagram or TS diagram. So we mentioned it clearly in the very first class that it is a reversal process only that we are able to represent through solid lines or curves in the PV plots or TS plots or any kind of this property diagrams in the from the perspective of classical thermodynamics. Okay, but as we know, in real life cases these irreversibilities are unavoidable and they actually persist. So there has to be some way through which we can represent or understand or quantify these irreversibilities. Okay, so Professor Anand in these lectures he mentions about some way that through which we can, I must say, find a quantifiable quantity that takes into account these irreversibilities. Okay, so that's what we look into now. So in the case of turbines, we saw that the primary task of turbine is to produce work, by expanding the working fluid. Basically, in the case of in expanding, by expanding I mean that causes the pressure to go down. Okay, so we have seen when we are studying about the Rankine cycle, we saw that when the working fluid passes through the turbine, the pressure of the working fluid goes down, and basically it expands, and it is that this expansion that produces the net work. Okay, so if this, and we saw it in the case of Rankine cycle, it was represented by a straight line. Okay, so this straight line would, in this TS plot, would represent a isentropic expansion. Okay, so if you recall in the standard lecture, I mentioned in the TS plots, these vertical lines would represent isentropic processes. So this expansion through a turbine, if it is done to a reversible path or in a reversible manner, it represents an isentropic expansion that has been shown here, and that is what we have been considering till now. But in the case of in the presence of irreversibilities, this the expansion to turbines is not isentropic, but indeed it is done to a irreversible path as shown by this red dotted line. Okay, and here you can see that if we consider the net change in the entropy, that is say through 1 and 2 and say 2s and say 1 to 2, you can see that the net change in the temperature, at least if you look into a temperature, if you consider the temperature T1 and T2s and T2, you will see that the net change in the temperature is indeed lower in the case of a reversible, in the case of the irreversible case. Okay, so now you can think in a way that then you initially told that the irreversibilities can hamper the performances of these thermodynamic devices. Then why does the change or the network is greater in the case of turbine? So the main thing to look into here is that this turbine is not a work consuming device, but indeed a work producing device. Okay, so our desire would be to get as much as work to be produced from this turbine, but as you can see here, because of the irreversibilities, the net work produced indeed gets lowered because of the irreversibilities present in the system. That's why the net work produced is lower compared to the net work that could have been produced if the system was expanded in a reversible manner. Okay, so that's the catch here. Okay, the desired output becomes affected because of these irreversibilities. So if you consider I hope this discussion is clear. Again, we will define it in the following discussion, but I hope this is clear. So we will see similar plots for different devices as well, but I hope that this is clear. Okay. So from the first law we get that basically since it is a flow device, so we have to consider a steady flow energy equation, take into account the change in enthalpy as well. So we get the steady flow energy equation written here. Okay, so it is d by dt is equal to q dot minus w dot plus mi times hi plus vi squared by 2 plus gzi minus me dot he plus v squared by 2 plus gzi, considering only single inlet and outlet. Okay, then since there is it's a steady flow process, then d by dt term would be equal to 0. Considering the turbine to be insulated, effectively insulated, then the net heat interaction will also be 0. Okay, also then the only term that we are left with is the net work done, which is the important parameter that we need to take into consideration, and the energy flux terms. Okay, so from the mass conservation we see that for single inlet and outlet we get mi dot is equal to me dot is equal to m, say a generic value for the mass flow rate. Okay, considering these two to be equal, so we can replace this mi dot and me dot by m dot. Then considering that the change in the Ke and the kinetic energy and potential energy is negligible. Okay, I will again try to reiterate. It does not mean that there is no change in the kinetic energy and the potential energy. There might be some changes, but considering the fact that the net change in enthalpy is so much more than the change in the kinetic and the potential energy, that's why we can effectively disregard them. Like the magnitude of change of the kinetic and potential energy is very very low compared to the magnitude of change in the enthalpy. That's why we are disregarding them. Okay, so considering all these assumptions, we can finally write that the net work produced by the turbine can be written as W dot is equal to Hi minus He. Okay, so this was already discussed, but still we have just gone through them once to get the expression for the net work produced by the turbine. So if the work done is produced in a reversible manner, from the diagram we can write work done reversible as H1 minus H2S, where H2S represents the enthalpy at point 2 if it is achieved through a reversible path. Similarly, the work done irreversible is represented as H1 minus H2, where H2 is the enthalpy uh, obtained if the expansion was done through a irreversible manner. Okay, so the isentropic and efficiency is the quantifiable parameter that is used to understand these irreversibilities. That is defined as the ratio of the actual work done divided by the reversible work done. Okay, so the actual work done would indeed be the irreversible work produced considering the real life scenario. So that will be actual work done. So it would be H1 minus H2 divided by H1 minus H2S. And since we know that the work produced by this reversible part is always greater than the work produced through this irreversible part, so this efficiency would always be less than 1. Okay, but it's always not the way. It's not always not the case that the work actually is always the eccentric enthalpy is not always defined like this. Okay, so we'll see in the case of compressor or this work consuming devices, this ratio is reversed. Why we'll again see, but that's the thing. Okay, it's not a generic efficiency term that we have defined till now, that eta is equal to work net by the Q input. That is a generic measure for all kind of cycles and thermodynamic processes, but here it's something that we define depending on the device that we are considering. Okay, so I hope it is clear till now. I will if required I'll wait for 1 minute. If there is a doubt, may ask, or else we can proceed. Okay, so we can. It seems we can then proceed. So there was. So from this discussion, we come to an understandable conclusion that this entropy increases in an irreversible process. Okay. So it's a statement that has been thoroughly explained and discussed by Professor Anand in the lectures. So I'm not going to go through them. Not going through a thorough reasoning for this particular statement at this point of time, but it's something that you can intuitively try to understand yourself. Like think, like why irreversibilities always increase the entropy and not decrease the entropy. Okay, so there has to be some reasoning behind that. You can try to think from your own way right now, but it's a statement that has already been thoroughly discussed in the lectures, so I will not dive deep into it at this point of time. Of course, in the consequent part of this today's discussion, we'll get some examples where that will thoroughly explain or prove this statement. But at this point in time, I would just like you to try to understand or try to think why that's the case. Okay. Like why the increase in entropy uh, is always associated with the irreversibilities in the processes, and how the increase in entropy can be one way or another be related to the reduction in the efficiency of these thermodynamic devices or thermodynamic processes in general. So it's something that you can start to think right now, but till then, let us proceed. So from the process inequality, there is this relation. Let me just see this relation. We know that the cyclic integral of this del q by t is always less than or equal to 0. Okay, it is equal to 0 for a reversible process and less than 0 for an irreversible process. Okay, so it is something that we have thoroughly discussed and proved in the last two lectures, and it's one way or another a very good way to, I will not say it's the only way to look into the second law of thermodynamics, but it's one way, it's one of the very good ways to understand this second law of thermodynamics in a quantifiable manner. So there is an equation, a well-known equation for this first law, that is the, I will not say the only equation, but it's a very popular equation. It is the net heat transfer is equal to the net work transfer plus the net change in the energy of the system. So there is an equation, a quantifiable equation for the first law. But for the second law, we started with defining two statements that were the clauses statement and the Kelvin-Planck statement to understand the second law. And again, we went through series of examples of, say, reversible heat engines, then irreversible heat engines, then heat pumps, and examples of them to understand the second law. But I would say like it is the process inequality that gives one way or another a good quantifiable way to understand the second law of thermodynamics. Okay, it's just my perspective, and I feel it's again should be quite well understood, but still you can just look into it why it's so. Okay, so consider this TS plot. Okay, and there are again some processes been shown, that is a cyclic process from 1 to 2. Okay, so the part 1A2B1 represents a reversible part, and process 1A2C1 represents a irreversible part, especially through point 2C1. That is, from 1 to 2 it is reversible, but from 2C1, that is from 2 to back to 1 through C, it is achieved to a irreversible part. Okay, so that is why it is shown to a dotted line. Okay, so if you go to path 1A2B1, that is the reversible part, we know that the cyclic integral of del q by t should be equal to 0 from the closest inequality. Okay, so we would have integral of dqa by ta from 1 to 2 plus integral of dqb by tb from 2 to 1 to be equal to 0. Okay, from closest inequality for a reversible process or reversible path. Now, for process 1A2 from path 1A2C1, that is this path. Okay, we know that from closest inequality, cyclic integral of this del q by t cyclic integral of del q by t should be less than 0, because there is an irreversibility in part C. Okay, so we can write cyclic integral of we can write integral of del qa by ta from 1 to 2 plus plus integral of del qb by tb integrated from 2 to 1 should be less than 0 for a irreversible process. Okay, since the process is irreversible, so this should be less than 0 from the closest inequality. Okay. But we have shown that this change in entropy, that is ds, is equal to del q reversible by T. Okay, that is defined for a reversible process. Okay, and we know that since S entropy is a state function or a point function, the cyclic integral of this point function should be equal to 0. Okay, it only depends on the point. So if you go from 1 to 2 and back to 1, the net change in entropy has to be 0, irrespective of whether the process is done through a reversible or a irreversible manner. Okay, so even though, as you can see here, I have written it clearly, even though we have followed a irreversible path from 1a to c1, the net change in entropy is still equal to 0. Okay, but you should know that this del q by T does not represent entropy in itself. Okay, it is the change in entropy only for a reversible process. But if the process is irreversible, then cyclic integral of del q by T does not essentially represent the change in entropy. Okay, that's why it is less than equal to 0. So don't confuse this del q by T, the parameter del q by T, to be equal to or to signify the change in entropy. Okay, it is only defined for a reversible process. Okay, so from these equations we can conclude that this change in entropy or ds is in general always greater than del q by T. Okay, and it's only equal to del q by, if the equality will only persist if this process is done through a reversible path. Okay, that's why this, do not try to equate or associate the entropy to be in general to be equal to del q by T. Okay, so this part and this discussion is very important, and you may, like, once I share the notes, or if you get the PowerPoint presentation by Professor Anand, I would suggest that this part you try to thoroughly understand, like why here I say it is equal to 0 but here it is less than 0. It's primarily because this entropy and this cyclic del q by T are not equivalent. Okay, that's why. So entropy is equal to the reversible heat transfer divided by temperature, and not equal to the cyclic integral of del q by T. Okay, because del q by T in this case is also considered for reversible process, irreversible process as well, and in that sense it is not equal to the change in entropy. Okay, I hope it is clear. I feel that it might seem a bit confusing right now, but if there is any doubt you can ask. I'm open to discuss, but it is something that you need to understand. Okay, so if there is any doubt, if you may ask, or even after the recording as well, after the class as well, if after watching the recording you may put in the discussion forum, but it is something that you need to understand, so I will emphasize upon this one. So I hope then it is clear. So we can say that from these two equations and from this definition we can say that in general the change in entropy is greater than del q by T, and it's only equal to del q by T if this change in if the heat transfer is achieved through a reversible manner. So now if we integrate it, not a cyclic integral but a general integration from say point 1 to point 2, then we can write the change in entropy from 2 to 1, that is S2 minus S1, is greater than the integral of del q by T from 1 to 2. Okay, so this is again one of the important equations they need to remember. So don't confuse this one with the closest inequality. Okay, closest inequality is defined for a cyclic integral, but this definition of the change in entropy for a general process is not a cyclic integral. Okay, it's general integral from say point 1 to point 2, where we say that the change in entropy for S2 minus S1 is greater than the integral of del Q by T from point 1 to 2. Okay, so we can write in terms of now irreversible heat transfer as well. Like if the heat transfer is irreversible, then the change in entropy ds is greater than del Q irreversible by T. So it will be equal to ds if it is reversible heat transfer. So considering the fact that there can be irreversible heat transfer as well, then we can make the equation write the equation in a more generalized manner, that ds would be greater than or equal to del Q by T, or S2 minus S1 would be greater than or equal to integral of del Q by T from 1 to 2. I think I need to mention the limits as well, from 1 to 2. Okay, so okay, so let me go back again. I think I found a way that will help you to understand this in a better manner. Okay, so say if you consider equation 1 and 2, so if you consider this as 1 and this as 2, considering all the definitions, if you subtract 2 from 1, it is 1 minus, take 1 minus 2, then you will get this part, let me just write it. So yeah, this part will get cancelled out because these two are the same, done to the same part A. So we will be left with integral of 2 to 1 from del QB TB minus integral of 2 to 1 del QB TB. Say it is, oh yeah, I'm sorry, it should be C, that's why it is complete. It is C. Okay, del QC TC and del QC TC. Okay, so yeah, to be, yeah, and if you compare them, then you will see that since the presence of this term is causing this integral to be less than 0, then it will imply that this integral of del QB TB, yeah, less than 0, and if subtract it, it becomes greater than 0. So we are left with greater than 2 to 1 del Q C by TC. Now since this is done to a reversible manner, okay, it's done to a reversible part, it represents the change in entropy. Okay, so it would be S2 minus S1, since it is a reversible process. Okay, so I will write it reversible, since reversible process. So S2 minus S1 would be, it is then this it is then it defines the change in entropy is greater than S2 minus S1 is greater than 2 to 1 del P0 TC. Okay, I hope this is clear now. Okay, so this again is a very important equation to remember. So we can write that I hope it is clear till now. Uh, if required, I will stop, or else if there's any doubt, you may ask, or I will proceed. Okay. Uh, so Professor Anand mentions that for an isolated system, the net change in entropy is greater than or equal to zero. Okay. So this was one of the important statements that were discussed by Professor Anand, because in the case of an isolated system, there is no heat transfer. This delta Q is equal to 0. Then there is no mass transfer as well. There is no mass transfer as well, and the only way through which the entropy of the isolated system can be increased is through the presence of internal irreversibilities. Okay, like if the I would say if the system if there's irreversibility within the system itself, then that internal irreversibilities can change or increase the entropy of the system, because we know that since from the definition of entropy, that is ds, say if we consider for reversible heat transfer, it is del q reversible by T. Okay, so since there is no heat transfer now, so there is no way the entropy of the the entropy of the insulated system or the isolated system can be increased via heat transfer. Since there is no heat transfer, so the entropy of the isolated system cannot be increased through that. So the only way through which the entropy now can be increased is if there are some internal irreversibilities in the system. Okay, so that's why we can write that the net change in the entropy of the universe, I will show you why. Okay, the net change in the entropy of the universe, it is delta S system plus delta S surrounding, is equal to the net change in the entropy of the universe. Okay, and why I am trying to correlate these things is because the universe itself, in many of the textbooks or by many of the authors, can be considered as an isolated system itself. That is, it is the internal reversibilities. Like if we consider the universe as an isolated system, okay, then we can apply the same analogy here as well. Like we can apply the same analogy between an isolated system and a universe. That's if there is no interaction between the anything beyond the universe and the universe, anything inside the universe, then the only way the entropy that can be increased is through internal irreversibilities. And now these internal irreversibilities that we are discussing are all the activities that occurs inside the universe. That is, all the, say, the flowing of a river, okay, the exhaust of through a car, or flying of a bird, or the very existence of us humans or living organisms who breathe in oxygen, then release carbon dioxide, then all these activities, say, or the photosynthesis that is achieved in the plants, and how they make sugar out of the sunlight, all these activities can contribute in the increase in entropy. Okay, and it is these entropies, this increase in entropy, that can affect the entropy of the universe, which is in itself is an isolated system. Okay, so I hope you are able to understand this, and I think I'm going beyond the scope of this course by giving the analogy between of an isolated system in the universe. But this is indeed what describes the second law of thermodynamics in the largest possible way, or in the best possible way. Like why the entropy of the universe keeps on increasing. Okay, if our universe would not have been an isolated system, like if there was a way that the universe could have interacted beyond its boundaries, then the entropy of the universe could have reduced also, because if there is a net heat transferred out of this universe, then the magnitude of the change in the entropy because of the heat transfer, that is this one, may outweigh the net change in entropy because of all these life activities. Okay, life activities or this astrophysical activities that occurs in the space. But it's not the case, since there is no interaction of anything beyond the universe and the universe itself. So the only way, the only thing or things that can increase or affect the entropy are all the things that are within the universe, all the activities that are occurring within the universe, and that's why we see that the net entropy of the universe keeps on increasing. Okay, so there is a very good, let me just give you as an side activity if you want, there's a very good YouTube video by a channel known as Veritasium. Okay, it's a very popular YouTube channel, and it's a must for all the science students or science geeks who like science topics. So there's a very good YouTube video by Veritasium on entropy. I suggest that you go through it once. Okay, and then I think you'll be able to appreciate or understand the beauty and the scale of this second law of thermodynamics in a very good way, and you will be able to appreciate why this second law is so important and so much applicable in the scientific world, okay, or in the world in general. Okay, so I will suggest that go to the video once. It's around say half an hour long, if I'm not wrong. It explains everything that we have discussed till now in a very, very beautiful and elegant way. Okay, you will enjoy it for sure. Okay, yeah. So just give me 1 minute. We will try to proceed further. I think what we have for discussion is, if I'm not wrong, just give me 1 second. It's now different expressions for a compressor and a nozzle, and then about entropy generation. Yeah. So we are left with 2 topics to discuss. Then we'll start the the problem solving part. Okay. So just give me 1 second. Oh, sorry. Yeah. So let us proceed. Okay. So till now we have discussed about the change in the not change in, but we have seen the expression for the work done from a turbine. Okay. Well, now let us shift our focus to a compressor, which we all know is a work consuming device. Okay. Now we will see how these things change. Okay, but the concept remains the same, but the way in which we try to visualize these concepts shifts a bit. Okay, so if you recall, when we discussed about this Rankine cycle, there was a component of the Rankine cycle, that was the pump, where the fluid was pumped to a boiler at a very high pressure. Okay, so it essentially increased the pressure, which indeed resulted in a high boiling point of the working fluid, which gave us a higher range of temperature heat input, which indeed increased the efficiency of the Rankine cycle. So the essential task of the pump was to increase the pressure, and indeed through that increase in pressure, increase the enthalpy of the working fluid. Although the increase in enthalpy was not that much, but it was still there. Okay, we could see that there was a discernible change in the enthalpy because of the pumping of the fluid from lower pressure to a higher pressure. So if you consider the working fluid to be, say, an ideal gas, then this, I'm just giving an example, it does not has to be an ideal gas, but I'm saying that the change in enthalpy becomes solely the function of a temperature. Okay, so let us look into it. So we saw that again we represented this increase in the enthalpy through a straight line in the TS plot, given that it was a reversible process. So it was represented as an isentropic process in the TS plot. Okay, but because of the irreversibilities, the line that represents the increase in the enthalpy now shifts to 2 from 2s, okay, where 2s represents the enthalpy achieved through a reversible process. The discussion again similar to what we have discussed in for the case of turbine, so it's similar, but now the line shifts in the case of the reversible part. So now here you can see that if you just again draw a dotted line here and here, you will see that the change in temperature from point 1 to point 2 is greater than from point 1 to point 2s. Okay, so the work reversible is given by H1 minus H2s, which is, if you consider a ideal gas to be the working fluid, then you can simply write it as Cp T1 minus T2s. Okay. Similarly, if it is achieved through a irreversible path, then actual work done becomes H1 minus H2. These points H1 minus H2, then you can write it equal to Cp T1 minus T2. Okay. So I'm saying that, of course, in general, you cannot really visualize this Rankine cycle to operate on an ideal gas. It's the main reason that why we define Rankine cycle is to understand the steam turbines. So not just steam, but the steam power plants or thermal power plants. So the working fluid is essentially water, which does not follow this relation. Okay. In general, of course, if it is done through a constant pressure process, then this relation is valid. But in general, this relation is not valid for water. Okay, but still, in that case as well, if you consider the water to the working fluid as well, then also you will see similar curves. Okay, but in that way, in that sense, now the relation would be modified. It will basically be integral of Cp dt in a way, but the very concept of the increase in the work input because of the irreversibilities in the thermodynamic process would still persist or will still remain in the case of water as well. Okay, that's what I wanted to show. But considering the working fluid to be an ideal gas in this case is essentially to represent this isentropic efficiency in the case in the form of temperature, or to just to simplify our discussion. Okay, so that was the main goal for considering an ideal gas, but it's not a generalized case. That's what I wanted to emphasize. Okay, so again we try to define the isentropic efficiency for this compressor. So now the thing is now we need to consider the lower work. So we see that the actual work input now here is lower than, the isentropic work input is lower than the irreversible work input. Okay, so now we can see that the irreversibilities in the process has caused the work input to achieve the same output to be greater than the reversible work input. Okay, so that's how now irreversibilities in the process has affected the work input in the case of a compressor. So the actual work input has now becomes more because of the reversibilities compared to the reversible work input. So that's why the isentropic efficiency can be now written as H1 minus H2s, that is the reversible work done divided by the actual work done. Okay, and if you consider it to be a function of temperature only, or it to be in the working fluid ideal gas, you can represent it in terms of the ratios of temperature change as well. So we can write T1 minus T2s or T1 divided by T1 minus T2, which will be given by the ratio of the reversible work done by the actual work done in the case of a compressor. Okay, so I think you get it now, like how to understand this isentropic efficiency, concept of isentropic efficiency. Okay, so now let us just, the final device is the nozzle here again. So nozzle, if you recall, is a device that's used to change the velocity. Like specifically, if you consider a working fluid to operate in the subsonic regime, I sometimes feel very sad that I'm introducing separate concepts right away, subsonic and supersonic, which are not at all related to the topic that we're discussing till now, but I feel that some viewers or some students or even professors who are attending the sessions may be quite what to say, critical about using these terms because of the concepts on which these nozzles and devices are working. That is, this nozzle increasing the velocity of the fluid is only valid within the subsonic regime. Like if the flow becomes supersonic, then it works as a diffuser. Okay, so I don't think it's usually essential for all the students who are attending the course for the first time, but still, if there are some viewers who are quite critical about the concepts and who would like me to emphasize on that as well, that's why I am saying that. Okay, so I'm sorry if these topics may seem to be put right away in front of you without any pre-discussion, but just for the other viewers who are critical about these kind of concepts, I think I must just let them know as well. Okay. So in a subsonic regime, the main task of this kind of devices, that is nozzles, is to increase the velocity of the working fluid. Okay, so in that case, you may now understand that the change in the velocity would become your crucial parameter. So we cannot directly disregard the change in the velocity right away that we have been disregarding till now for all the devices that we have discussed. So change in the velocity or the change in the kinetic energy in general becomes a crucial parameter for this kind of devices. Okay. So again, now if we start with the steady flow energy equation, because since it's a flow device or a control volume through which the flow passes and our focus remains intact within the boundaries of the device, so we have to use this steady flow energy equation for understanding these kind of devices. So again, we write d by dt is equal to q dot minus w dot plus m dot times hi plus vi square by 2 plus gzi minus m dot he plus v square by 2 plus gze. Now you see m dot I have not changed as mi and me because if we consider a steady flow process, and of course this nozzle has to be of single input and single output, then we will get that mi dot would be equal to me dot equal to m dot. Okay, so use the same argument here. So now since since it's a steady flow process, then the d by dt term or a time derivative term would be equal to 0. Also, if we consider nozzle to be insulated, then q dot term will also be equal to 0. And since nozzle is not usually used as a work producing or work consuming device, it's just a device used to change the flow velocity, so the net work interaction is also equal to 0. Okay, there is no shaft work or PdV work in these kind of devices. So the only term that becomes of importance is the energy flux terms. Okay, that is basically these terms. Okay, now if you come, and in general, always again, nozzles are usually like, what I can say, in general perspective, nozzles are usually placed in a horizontal way where there is no change in the potential energy. But again, nozzle can be used in a tilted manner, in a vertical manner. Of course, those are the scenarios, but then also the change in the potential energy is, or the magnitude of the change in the potential energy is usually much lower than the change in the enthalpy and the kinetic energy. That's why we are disregarding them just for the simplification of the Gauni equation. So the equation that we are left with is hi minus he is equal to ve square plus ve square by 2 minus vi square by 2. Okay. Now again, since I mentioned that change in the work of the nozzle is primarily to increase the velocity at the outlet. That is, if the flow comes through it as an inlet and goes out through it, the nozzle will increase the velocity. Okay. So in that case also, for a further simplification or for a first order approximation, you can consider that the magnitude of the exit velocity is usually higher than is lot higher than the magnitude of the incoming velocity. Okay, so in that way, as a first approximation, we can also disregard the magnitude of the incoming velocity as well. So if we consider that, then we can write this equal to 0. Then we have hi minus he is equal to ve square by 2. Okay. So for example, if the incoming velocity is at 1 meter per second and the outgoing velocity is at 3 meter per second, then not say 3, let us say 10 meter per second. Okay, it's just an example for you to understand. Now since it is a square of the velocity, then the incoming kinetic energy will become say 1 by 2. Okay, and the outgoing kinetic energy would become 10 square by 2 or 50. 50 minus 1 is 14, 49, which is all 50 minus 0.5, which is 49.5, which is almost equal to 50. So that's why we can disregard this term in that way. Okay, just in the perspective of magnitudes. So in the case of nozzle as well, we define the isentropic change in the enthalpy as H1 minus H2S, or Cp T1 minus T2S, and actual change in the enthalpy to be H1 minus H2 or Cp T1 minus T2. Or this isentropic efficiency of the nozzle is represented by H1 minus H2 divided by H1 minus H2S, or V square by V square S. Okay, so that's how we represent the isentropic efficiency of the nozzle. Okay. Okay, so I think I can skip this part, but still I'll just briefly go through it. This part. So the expression for the work done by a pump. So I think it's already been discussed, but still, like, there might be some problems in the assignments where you may need to recall the expression for work done through a pump. So we know that the work done from a pump is again represented by this expression, that is Hi minus He, if we consider an isentropic pump. Now from the thermodynamic property relations, we get Tds is equal to dH minus Vdp, and since the entropy change is an isentropic pump, so ds term will be equal to 0, so Tds will be equal to 0. So we have dH is equal to Vdp. Or the net work done would be minus Vdp, in the sense that it is a work input to the system. So the net work done will be integral of this minus Vdp. Now since the change in the specific volume of the fluid is in general very less, is almost negligible, so that's why we can take this specific volume to be out of the integral and just integrate the change in the pressure. So we're left with the work done from a pump to be equal to minus V times P minus Pi. Okay, and this is the expression in general that we use to find the net work input to the pump when we consider these Rankine cycles or these steam cycles. Okay, so yeah, I think this is the last part of the theoretical discussion for today's class. A brief discussion on the entropy generation. Okay. So yeah, let us try to go through it. Okay. For this discussion again, let us start with the equation that we have discussed. Again, this is not the process inequality. Okay, but this is the equation that we have mentioned, that for an isolated system, the net change in entropy is always greater than or equal to 0, and the relation between the change in entropy and the ratio of heat transfer by temperature is usually given by this equation, where this equation is valid when, or this is equal to del Q by T when the net heat transfer is done through a reversible manner. Okay, so from that we can write ds to be equal to del Q by T plus some additional term. Okay, since ds is greater than or equal to del Q by T, then it would mean that ds should be equal to del Q by T plus some additional positive term. Okay, positive term, it has to be positive, so that this greater than symbol can be changed to an equality by considering del Q by T plus some additional input to this equation. Okay, which has to be positive. Okay, that itself shows us that the entropy generation is always greater than or equal to 0. Okay, so so if this is irreversible heat transfer, okay, where the greater than equal to sign will still remain valid. So we can write TDS is greater than, I think to remove confusion, I think I should write TDS is greater than del Q irreversible, okay, or TDS should be equal to del Q irreversible plus T times delta S generation, okay, delta S generation, okay. I hope these equations are making sense, okay. So we know that from this relation, that is delta S, sorry, ds is equal to del Q reversible by T, we get that del Q reversible is equal to TDS, okay. So we can replace this TDS by del Q reversible here, so we can write del Q reversible is equal to del Q irreversible plus T times delta S gen, okay, or del Q irreversible as del Q irreversible minus TDS gen, or del Q we can replace this del Q irreversible by again by TDS, this one, so we can write del Q irreversible as TDS minus T delta S gen, okay. So this is again an important equation. Then from the first law, sorry for that pause, I was just trying to understand the equations properly. So from the first law, we get that du is equal to dq is equal to du plus delta w, okay, or you can write this for the irreversible process as well. It is del q irreversible is equal to du plus delta w irreversible, okay. See, in the case of first law as well, this is valid for a reversible process, okay, and this is for an irreversible process, but the change in the internal energy would remain the same with, even though if it is done to a irreversible part. So that's why the change in the internal energy remains intact, okay. So T del Q irreversible is equal to du plus del W irreversible, okay. Now we know that from that TDS is equal to du plus PdV from the thermodynamic property relations, or du is equal to TDS minus PdV, okay. So we can write du as TDS minus PdV plus delta W irreversible. Now TDS minus PdV would be equal to delta Q reversible minus delta W reversible. Why? Because of this relation, okay. So we can write delta W reversible by delta Q reversible is equal to delta Q reversible minus delta W reversible plus delta W irreversible, okay. I hope you are following the we are following the equations, okay. Why this can be done is discussed here, okay. The change in the internal energy is valid for both reversible and irreversible processes, and the change in internal energy is independent of the process through which it has been achieved. That's why this change in internal energy is valid for both reversible heat transfer and work transfer, as well as irreversible heat transfer and work transfer, okay, considering the change occurring through these two state points. So because of that, we can write this delta Q irreversible as delta Q reversible minus delta W reversible plus delta W irreversible. Or if you rearrange this equation now, I think I have to write it here for better clarity. Delta Q irreversible. Okay. So now if you rearrange this equation, you can write delta Q reversible minus delta Q irreversible to be equal to delta W irreversible minus delta W reversible. And since we know from this equation that delta Q reversible minus delta Q irreversible is equal to T ds gen. Okay, so I think I should write it somewhere here. This would give you delta Q reversible minus delta Q irreversible to be equal to T delta S gen. So from that we can write delta Q reversible minus delta Q irreversible to be equal to delta W irreversible minus delta W reversible to be equal to T ds gen. Okay, or if you just consider this part, we can write delta W irreversible to be equal to delta W reversible minus T ds gen. Okay, or if we continue this, we can write delta W reversible is equal to delta W reversible minus T ds gen, where T ds gen will represent the lost work. Okay, so we mentioned that the work in the case of say turbine, we saw that the work produced through an irreversible path was lower than the work produced by the reversible path, and that's why it is shown why there is a work loss in the case of a irreversible process. Okay, see this delta W reversible from we are considering from the first law. Okay, and since the sign was positive, it would imply that it was a work done by the system. So all these delta W that discussed here are the work done by the system. Okay, so this delta W irreversible represents the work done by the system through the irreversible path, or delta W reversible represents the work done by the system through the reversible path. So we can clearly here see that the work done by the same system through the irreversible path causes a work loss that is given by T delta S gen. Okay, there is a net loss of work. Okay, so I hope this is clear till now. Let us we'll just discuss the final part. I think it's the extent of irreversibility again. So I think okay. So consider this diagram. Okay, this diagram for a cyclic process shown here. Okay, so this essentially represents a Carnot cycle. As you can see, this represents a Carnot cycle where the lower temperature limit as it is at T naught and the higher temperature limit is at T. Okay, and it produces a network W which is equal to Q, that is for a cyclic process. Okay, that's why Q equal to W for a cyclic process. Now the thermal efficiency of the Carnot cycle would be given by 1 minus QL by QH, or that will be equal to 1 minus T naught by TH, because T naught is the lower temperature limit. For cyclic process, we know that the cyclic integral of heat interaction and cyclic integral work interaction is equal to 0. For the Carnot cycle as well, this would be valid. Now the available energy is given by, for the above Carnot cycle, is given by T minus T naught times delta S. Okay, so that would give you the net available energy from the Carnot cycle, and the net energy that is unavailable for use, that is this part, is given by T naught times delta S. Okay, so there is a way through which we can represent this extent of irreversibility, that is given by I, that is delta W reversible minus delta W irreversible. Basically the available work that is for a particular Carnot cycle is given by I equal to delta W reversible minus delta W irreversible, or that is equal to T naught times delta S gen. Okay, and if there was a particular process that is not in line with your Carnot cycle, that is not as simple as the Carnot cycle, we can represent this unavailable energy as similarly as T naught times delta S, but the available energy part can be given by integral of T times delta S minus this T naught delta S. Okay, so if I'm not wrong, I think just we just look into it. If there are any further discussions on, yeah, of course, there are some further discussion on this available energy part, okay, or extent irreversibility in the later part of the course. So I think that then it will become much more clearer, but at least as an introductory part, these definitions are quite good. Okay, so right now you can just take it as a definition or as an understanding, but its further applications would be discussed in the later part of the course. Okay, in the last two remaining lectures, we will try to cover up a bit more. Okay, so for the last part, we look upon the energy equation for a just give me 1 second. Look upon the energy equation for a flow through a particular duct, okay, as given here, considering only single input and single outlet, single input, single outlet. The mass conservation equation can be represented as dm by dt is equal to mi dot minus me dot equal to 0, or mi dot would be equal to me dot would be equal to a generic mass flow rate m dot. Okay, then the energy equation can be given by d dt is equal to q dot minus w dot plus m dot hi plus vi square by 2 plus gzi minus m dot plus v square by 2 plus gze. Okay, then if we consider for steady state, the E by dt term would be equal to 0. If we consider it to be insulated, if there is, I won't say insulated, but if you say that there is no heat interaction in this particular system at all, then Q dot is again equal to 0. And since this kind of flow is not producing any kind of work, any kind of shaft work, then of course flow work is there. And if you recall, this flow work is incorporated in the enthalpy. Okay, so flow work is still there, but there is no shaft work or PdV work. So this W dot is also equal to 0. So the terms that we are left with is given by this equation. Okay, that is Vi square by 2 plus Gzi plus is equal to Hi minus He plus V square by 2 plus Gzi. Okay, basically all the terms in an energy flux terms are given. If these were equated, then we can easily cancel out the m dot term. Okay, so we are left with this equation. Now from the thermodynamic property relations, we get that TdS is equal to du plus PdV, or TdS is equal to dH minus VdP. Okay, the second thermodynamic property relation. Now for an isentropic process, okay, you see there is no, if there is no heat interaction and it is a reversible process, then we can write TdS to be equal to 0. Okay, for isentropic process, then dH would be equal to VdP, or dH would be equal to 1 by rho times dP. Now if we consider this rho, the density of the fluid to be constant, we can write delta H is equal to 1 by rho times delta P. Okay, basically if rho is constant, we will be able to integrate it. So the change in the enthalpy will be equal to 1 by rho times the change in the pressure. Now if you substitute this expression in the above equation, in this equation, you will get something like Vi square by 2 plus Gzi will equal to 1 by rho Pe minus Pi plus V square by 2 plus Gzi. Now if you rearrange these equations, you will get Pi square by rho plus Vi square by 2 plus Gzi will be equal to P square by rho plus V square by 2 plus Gzi. And it is one of the very popular equations in the fluid mechanics. If you know, it's known as the Bernoulli's equation. Okay, and the reversible perspective in the fluid mechanics can be considered through the fact that there is no this kind of equation is usually treated for in-viscid flow, where the viscosity is not considered. And in the perspective of fluid mechanics, the internal irreversibilities that can be generated because of the flow through this duct is because of the viscosity. Viscosity would generate boundary layers, would generate velocity gradients, which may cause this viscous dissipation, which can be taken as the internal irreversibilities that can occur when we consider viscosity of the flow. Since this equation is valid for in-viscid flows, like one of the assumptions that we use to derive this Bernoulli's equation, that's why this equation is valid when no internal irreversibilities are considered. Okay. So I hope it is clear till now. Now I think we can start the Q&A part. Just give me 1 second. I hope the question is visible. Okay. Then can try the first question. For an ideal gas on a TS plot at the same temperature, the constant volume curves have higher slope than constant pressure. Constant pressure curves have higher slope than constant volume process, or both constant pressure and constant volume curves have the same slope. So which of the following answers would be correct? Okay, we just discussed it in the start of today's discussion. A. Okay, so constant volume curves would have higher slope than constant. Yeah, that is correct. So thank you. The next question is a heat source at 1000 Kelvin loses 2000 kilojoules of heat to a sink. Okay, and case 1 is that the sink temperature is 300 Kelvin. Second case, the sink temperature is at 700 Kelvin. Which heat transfer process is more irreversible? Okay, or case 1, case 2, or is it same for both cases? Okay, so if you know, you can intuitively answer it as well, but if you want, you can calculate also the net change in the entropy of the universe for both the source and the sink, and see in which case the net entropy of the universe is change the entropy of the universe is higher. Okay. So if it is higher, then it will imply a more irreversible process. So you can try that out. I will say wait for 4 minutes, and then of course there is an intuitive way to look into the answer, but for many viewers, I think as an introductory course, it may be beneficial if we look upon a detailed solution. Okay. So I'll wait till 6:42, I guess, then we can look into the solution. A. Okay, so which process is more irreversible? So one of the answers that I get is case A, and that's indeed correct. Okay, but thank you for the answer, but I think it will be just beneficial for the other viewers as well, like how we are able to come to that conclusion. Okay, of course there is an intuitive way to look into it, which I will discuss once I look into the solution, but I think for now let us just try to look into the solution. Okay, so for that case we need to look upon the net change in the entropy of the universe. So in that case, our universe would be composed of the source and the sink, because these are two systems that are interacting with each other. Okay, so for case 1, the net change in the entropy of the, or total change in the entropy, is given by delta S source plus delta S sink. So we have Q source divided by T source plus Q sink by T sink. Now Q source would be the negative of the Q sink, because the energy is being transported from the source to the sink. The heat loss from the sink is the heat loss from the source is the heat gain to the sink. So since the temperature of the source is 1000 Kelvin and temperature of the sink is 300 Kelvin, if you do this calculation, okay, you will get the net change in entropy to be 4.667 kilojoule per Kelvin. Okay, keep this magnitude of this numerical value in mind. Now let us look in the second case. Same, S total, delta S total is delta S source by delta S sink. Then Q, it will be Q source by T source by Q sink by T sink. But the only change here is that the heat transfer is remaining the same, but the temperature of the sink now changes from 300 to 700 Kelvin. Okay, and if you do the calculation, you will get that the net change of the entropy of the total, that is the source in the sink, would be 0.857 kilojoule per Kelvin. And since the entropy change is higher in the case of case 1, that's why case 1 is more irreversible, or you can say vice versa, since the entropy change for case 2 is lower, therefore it is less irreversible. Okay, and the intuitive way to look into is that since the case 2 involves a smaller temperature difference, this makes it less irreversible. Okay, so if you recall, when we were discussing about these irreversibilities, we mentioned about a perfectly reversible heat transfer process. So I mentioned that in a physical sense, this perfectly reversible heat transfer process is not possible, because, or it will achieve through a very long process, primarily because we know that for a heat transfer to occur, we need a temperature gradient. That is, there should be a temperature difference, but it is the presence of this temperature difference that causes the irreversibilities to get imbibed into the systems. Okay, so greater the temperature difference, greater will be the irreversibilities during that heat transfer process. So if you would have recalled that statement, you could have easily told without even any calculation that since the temperature of the source remains the same and case 2 has a lower temperature difference compared to case 1, that's why case 2 will intuitively have a lower irreversibilities, and that's why answer A would be correct. That is, case 1 is more irreversible. Okay, so I hope that concept is clear. It was a tricky question, an intuitive where we can use your intuitive understanding to solve it, even doing any kind of calculations. Okay, so question number 3 is choose the correct statements. Okay, the increase in the entropy of the entropy principle implies that the entropy of any system cannot decrease. The entropy change of a system can be negative during a process. Entropy is never conserved. The entropy generation of a system can be negative during a process. So which of the following statements are correct? C. Okay. Okay. Just give me 1 second. I think. Uh, okay. So we need to, through all the topics that we have discussed till now, we need to look upon which of the following statements are correct from the perspective of the concept that we have discussed. Okay, so let us look into the first statement. Okay, the increase of the entropy principle implies that the entropy of any system cannot decrease. Okay, so again, this is not specifically correct because of the case that in general, if the first part it's not correct because the entropy of any system can decrease. Okay, if there is a heat transfer out of the system, the heat transfer, then the entropy can decrease. Okay, so this statement is incorrect. Second is the entropy change of system can be negative during a process. Okay, so this is correct in the sense that, as I mentioned, if there is a heat transfer out of the system, and even because of the heat transfer out of the system, if the magnitude of the entropy change because of the heat transfer out of the system is greater than the entropy generation because of this particular process, then the change in the entropy of the system may be negative, but since it is the entropy of the universe that has also it is the entropy of the universe that has to be always positive, then you will see that the change in the entropy of the surrounding will outweigh the change in the decrease in the entropy of the system, which will give us a net increase in the entropy of the universe. Okay, so that's why this statement is correct. Statement C, as you have mentioned, if I'm not wrong here, yeah, C is absolutely correct because we see that entropy is never conserved. So by conservation would mean that the change in the conserve means what? Like the energy is conserved. Like whatever energy input you give is the energy transfer has to be conserved by the very first law of thermodynamics. Okay, the net heat input is equal to the net work output plus the net change in the internal energy. So the net energy of the system is conserved. Okay, whatever energy input is given, either it is ejected out as in the form of work, or it is being stored in the system that causes the temperature of the system to go up. Okay, so one way or another, the energy is conserved, similar to mass. Like if there is a net flow through the system, whatever comes in goes out, or if there is some storage, then maybe the flow may be higher, but because there is no output of that particular fluid, then the fluid might get stored in the system. So in one way, again, there is conservation. But in the case of entropy, we do not see any kind of this conservation where the entropy transfer remains constant. We see that from the very definition of second law, that the entropy of the universe keeps on increasing, and since there is no way to provide any conservation to this to say thermodynamic property, so entropy is never conserved. Okay, and finally, the entropy generation of a system can be negative during a process. Okay, oh, and this one again is not correct. Why? Because it is entropy generation. Okay, entropy generation, if you recall from our discussions that in the last part of our previous discussion, that we saw that this entropy generation term is defined something like delta S is equal to del Q by T, it is irreversible, plus delta S gen. Okay, so in general, delta S is always greater than del Q irreversible by T. Okay, which is not the closest inequality but a consequence of the closest inequality. Okay, so to make this equation valid, to correlate this delta S and Q irreversible, to get an equation, we add a positive term delta S gen, which is the entropy generation. So entropy generation can never be negative during a process. Okay, so both B and C are correct. Okay, but if this question was again only for what is the principle of increase in, what is the increase in entropy principle? Okay, increase in entropy principle, then this statement would have been the sole answer. But we are asked to choose the correct option of all the concepts that we discussed till now. So both B and C are correct. Okay, I hope that is clear. Okay, so question number 4 is already, I think we have done it again and again, so it is similar to question number 1. So if needed, for the other viewers or students, I will put the solution in the PDF of the particular discussion that we have done, so it will include an answer. Okay, but for now, for the sake of saving time, and I will skip this solution. Okay, we have already discussed this in question number 1. Okay, and we have already discussed in the first part of today's class as well, so I will maybe skip this part. Okay, let us look in the next question. Question number 5. A heat engine receives heat from a source at 1200 Kelvin. I'll just try to underline important terms. 1200 Kelvin at a rate of 1200 kilojoule per second and rejects the waste heat to the sink at 400 Kelvin. If the power output of the engine is 400 kilowatt, the second law efficiency, okay, of the heat engine is okay. So this I think I need to discuss in a way that we have not formally discussed the second law efficiency. So this question, if it's okay, I would like to take it myself. Okay, so let's go to the question once again. A heat engine receives heat from a heat source at 200 Kelvin. Okay, so the TH is 1200 Kelvin at the rate of 1200 kilojoule per second and rejects waste heat to a sink at 400 Kelvin. Okay, so sink temperature is also given, and if the power output of the engine is network output is 400 kilowatt, the second efficiency of the heat engine is, you have to find this one. Okay, so I would like to take this answer. Maybe you can take the next question. Okay, so second efficiency or eta 2 is given by the efficiency of the actual engine or process divided by the efficiency of the ideal cycle or process. Okay, so the concept is that the efficiency of a particular cycle or process is usually defined by this expression. Okay, there is the net work output by the net heat input. But if the same process would have been an ideal process, then if we know temperature limits, then the efficiency of that particular process or cycle is given by this, that is 1 minus TL by TH. Okay, we have discussed this, both of them actually separately, and how they are different and when they can be same in the previous lectures when we discussed about reversible and irreversible processes, but we didn't formally introduce your second law efficiency. The second law efficiency is something given by the efficiency of the actual cycle, that is given by the net work output by the net heat input. This is generic efficiency formula for any kind of process, be it reversible or irreversible. But for an ideal case, for a reversible process, the efficiency is given by 1 minus TL by TH. So the ratio of them is give the second law efficiency. So we know in the question we got that the work output was 400 kilowatt and the work heat input was 200 kilowatt, it is kilojoule per second. So divided by 1 minus TL by TH, so the lower temperature limit was 400 Kelvin and the higher temperature limit of the source was 200 Kelvin. Okay, so if we do this, then we get 400 by 1200 is equal to 1 by 3, or 1 minus 400 by 1200 would be 2 by 3. So the second law efficiency in this case would be 0.5 or 50%. Okay, so it's actually it's not that difficult to evaluate, but since we have not discussed this concept in the class, I thought that it would be just better if I take this example myself. Okay, so maybe we can try the next question. Okay, I think for this I need to zoom out a bit. Okay, I think the question is still visible. You can try this part. Okay, a quantity of air undergoes a thermodynamic cycle consisting of 3 processes. Process 1 to 2 is a constant volume process, heating from P1 at 0.1 megapascal, T1 at 15 degrees Celsius, and V1 at 0.02 meter cube, and 2 at pressure of 0.42 megapascal. It's a constant volume process. Okay. Process 2 to 3 is a constant pressure process, or constant pressure cooling. Okay, constant pressure cooling. And process 3 to 1 is an isothermal heating to the initial state. Employing the ideal gas model with Cp is equal to 1 kilojoule per kg Kelvin, evaluate the change in the entropy of each process. Okay. So you can try this out. Maybe you can, I'll give you 5 minutes, maybe you can try it. It will be a bit lengthy, but I think it's a good exercise for the amalgamation of all the concepts that we discussed till now. The ideal gas law, expression for the change in entropy, everything we discussed. would be constituted within this question itself. So I think it's a good practice. So you can try, of course. After that, so after 5 minutes, uh, we can just look into the solution, and then we can proceed further. So the main task is to find the net entropy change for all the three processes. Okay, so you can try that out. Okay. Oh, sorry. So I think stopped screen sharing by accident. Just 1 second. Okay. Think I'm not able able to show my screen. Okay, so maybe I will try to rejoin. Okay, just yeah, please, yeah. I'm not able to show my screen. Just kindly wait. Okay, just kindly be in the class. I will try to rejoin. Yeah, maybe now I will be able to share the screen. Sorry for the inconvenience. Just not able to share the screen. Yeah. Okay, so I think we can proceed with the solution. Okay, so let us see how it can be done. So the PV and the TS diagram of the given processes can be drawn in this manner. Okay, process 1 to 2 is a constant volume heating. Okay, so it's given by this one, constant volume heating. So 1 to 2 would have a particular slope, if you recall. Then 2 to 3 is a constant pressure cooling, if I'm not wrong. It's a constant pressure cooling. Let me just go back to the question. 2 to 3 is a constant pressure cooling. 3 to 1 is isotope heating. Okay, so yeah, so 2 to 3 is a constant pressure cooling, so temperature will go down. Okay, but the slope, if you recall, would be lower than the constant volume process. Okay, that's why you've drawn it separately here. And finally 3 to 1 is a isothermal heating. Okay, so it will constitute a cycle, so it will go back to its initial condition. So 3 to 1 is an isothermal heating. So you may think it should be, it could have gone here as well, right? But heating, if you recall, would increase the entropy of the system, since it is del Q by T. If del Q is positive, entropy will increase. So 3 to 1, the entropy will increase and go back to its initial state. Okay, so that's how you draw the cycle. Now look, let us look into the values of these properties. So the initial pressure, that is P1, is 0.1 megapascal. Initial temp, it's a good practice when we deal with these cycles or air standard cycles to change the temperature scale to the Kelvin scale. It would be just suitable, and it makes it avoids a lot of mistakes. Okay, so T1 would be 15 plus 270 or 288 Kelvin, and V1 is 0.02 meter cube. So these are initial conditions, and pressure P2 is 0.42 megapascal. Okay, so since they asked us to find the net change in entropy, not the net change in entropy per unit kg, so we need to find the net mass of the working fluid. Okay, the net mass of air in this case. So considering air to behave as an ideal gas, which is generally a good approximation, but it is specifically being mentioned here in the question as well. So we need to consider it as an ideal gas. So we can write M is equal to P1 V1 times divided by R1 times T1. Okay, from the ideal gas law. So P1 is 0.1 into 10 to the power 3, converting megapascal to kilopascals for our ease of calculation. V1 is 0.02 meter cube. R is the specific gas constant for air, which is 0.287 kilojoule per kg Kelvin. That's why we convert pressure into kilopascal, so that all the units are consistent. And temperature is 288 Kelvin. So if you do that, you can get M, or the mass of air, is 0.024 kg. Now process 1 to 2, it's a constant volume process. Okay, so the parameters that are changing are your pressure and temperature. Okay, since you already know that final pressure P2, the task would be to find a change in the temperature. You will see why. So from this relation, this can easily be obtained from the ideal gas law. I will just give you a hint for this case only. For other cases, I will just skip the derivation parts. P1 V1 by R T T1 would be equal to P2 V2 by R T2. So V1 and V2 are equal, constant volume process, R is the specific gas constant, so we will get P1 by T1 is equal to P2 by T2, constant volume process. So from that you can easily find T2 as P2 by P1 times T1, or T2 as 0.42 by 0.1 times 288, or 1210 Kelvin. Now since it's a constant volume process, we know that the change in the entropy is given by, from the TDS relations, if you recall, if I just go back here, is given by this equation, right? So the derivation and the, what to say, the perspective behind this equation, you can go back in the previous lectures to revisit the previous lecture to see how this equation is obtained. But this is the expression for a net change in entropy for an ideal gas. Okay, but we just simplify the TDS relations, the thermodynamic property relations, to find the net change in the entropy. Okay, just for your reference. So since we are doing a constant volume process, the specific heat at constant volume would be an important parameter for us to consider. So we have to find CV. So CV would be Cp minus R from this relation, and Cp in the question they have asked us to take to be equal to 1. So from that we will get CV as 0.713 kilojoule per kg Kelvin. Okay. Now from this relation, the net change in entropy for process 1 to 2 would be given by S2 minus S1 is equal to mCv ln T2 by T1 minus R ln V2 by V1. Now since it's a constant volume process, this would be equal to 0 because V2 by V1 will be equal to 1, and natural log of 1 will give you equal to 0. So this would be equal to 0. So we are left with this term. Now all of these values are already known. So m is 0.042 times 0.713 times natural log of 1210 by 288. So, okay, or temperature at this natural log should always be in the Kelvin scale, or the absolute temperature scale. That's why I asked you to convert all temperature in the Kelvin scale. Then from this you get the net change in entropy from process 1 to 2 to be 0.0426 kilojoule per Kelvin. Okay. Now for process 2 to 3, we can similarly tell, if you just S3 minus S2, the net change in the entropy of the process can be given by this equation. Okay, I have messed up the indexing, so I'm just correcting it now. So it would be T3 T2. Okay, and there's again a negative of, or a positive of this pressure ratio in this plus some R ln P2 by P1. This term is there. Okay, I'm sorry, plus R ln P2 by P1. This term is there, but we are disregarding it because it's a constant pressure process. Okay, similar to this, we get another expression for the entropy change from thermodynamic property relations in terms of the enthalpy. So there we get a pressure ratio, and since it's a constant pressure process, we are just disregarding that part. Okay, so if you want it, you can keep it as an exercise to find that term and just start from the term itself, but for the solution I am just trying to skip that. Okay, now since this is a constant pressure process, again using the ideal gas law, we get V3 by T3 is equal to V2 by T2. Okay, again I have messed up because, oh no, it is correct only. Now we get T3 would be equal to V3 by V2 times T2. Okay, now since, if you recall, V2 would be equal to V1. Why? Because process 1 to 2 was a constant volume process. That's why we'll have, yeah, for that we have to find V3 as well. So let's find V3. Okay, I skipped that part. So I think I need to find V3 as well. Okay, sorry for that confusion. Okay. Yeah. So since process 1 to 3 was isothermal, if you recall from the question, we can write P3 V3 is equal to P1 V1, okay, or V3 is equal to P1 V1 by P3. And since process this 2 to 3 is an isobaric process, a constant pressure process, so P3 would be equal to P2. So from that you can easily get V3 is equal to 0.1 times 0.02 divided by 0.42 or 4.76 into 10 minus 3 meter cube. Okay, so that's how you can find V3. Okay, so now we will use this V3 to find the temperature, because see, the end goal is to find a temperature, because it is a change in temperature that will give you the change in the entropy for these special processes such as this constant volume and constant pressure processes for an ideal gas. That's why the end goal here is now to find the temperature. So we find temperature for the process 3, that is our state point 3, that is V3 by V2 times T2 from the ideal gas law. Now V3 is 4.76 into 10 to minus 3 divided by V2 is 0.02 times 1210, that is your T2. From that you will get T3 as 288 Kelvin. Okay. One more crucial thing that we can get from this is that since process 3 to 1 is an isothermal process, T3 is equal to T1. If you recall, we get the same result, right? Initially we told that T1 was equal to T288, we got a similar value from this calculation as well. Okay, so the net change in the entropy, just give me 1 second. Estimates S2 would be mCp ln T3 by T2, mass is 0.024 times Cp is 1 times natural log of 288 by 1210 or minus 0.03445 kilojoule per kg Kelvin. So now you can see that there you get an example where the entropy change of the system is negative because the heat is, it is a heat rejection process. If you recall, it is a constant pressure heat rejection. So since heat is going out of the system, the net change in the entropy is negative. Okay. For the final process, this process 3 to 1, which is an isothermal process, we get that the net change in the entropy is given by S1 minus S3 is equal to minus mR ln P3 by P2. Okay, so again this is the term of the remaining term of this equation, this part, that this would actually be mCp ln minus mR ln P3 by P2. Okay, so since temperature is constant, the first term here is now removed. We are left with the second term, which contains the pressure terms. So we're left with S1 minus S3 to be equal to mR ln P3 minus P3 by P2 or 0.024 minus times 0.287 divided by natural log of 0.1 divided by 0.42. If you do that, you will get it to be just give me 1 second. Okay, I think there has been a mistake here, so that's why I'm just give me 1 second. Okay, so then I think it should be positive. Okay, so let me just try to derive it right away here. Okay, so it will be better. So we have, sorry for this confusion. Okay, I think I messed ds minus vdp, or ds is equal to cp dt minus v vdp by t. Now PV is equal to RT, or V by T will be equal to R by T. So ds would be Cp dt by T minus R dP by P. So if you minus S1 will be Cp ln T2 by T1 minus R ln T2 by T1. Okay, so yeah, that's why that was the mistake here. It is correct only, but I have changed the pressure. So pressure P3 would be 0.42 because P3 is equal to P2, and pressure P1 will be 0.1. Now it is correct. So the net entropy change is minus 0.00988 kilojoule per Kelvin. Okay, so I hope this was clear. Okay, sorry, I thought I just messed up the equation, but this is the way to do it. I hope it is clear. Okay, so let us go to the last question. Okay. This is the question. A system has a heat capacity at constant volume Cv is equal to AT square, when A is equal to 0.042 joule per Kelvin cube. The system is originally at 200 Kelvin and a thermal reservoir at 100 Kelvin is available. What is the maximum amount of work that can be recovered as the system is cooled down to the temperature of the reservoir? Okay. So I think you can try it out. You can draw the schematic diagram of the system. I hope the question is clear. You can try it out once. After some time, for the sake of saving time, I think I have to directly look into the solution. Okay. We need to find the maximum amount of work that can be obtained when the system is cooled from 200 Kelvin to 100 Kelvin. Okay, so that's the main goal. Okay, so I think if it is fine with all of you, I think for the sake of saving time, I can look into the show the solution right away. Sorry if it is inconvenient. Sorry for inconvenience, but I think it is already past 2 hours. So I think I can share the solution once. Then if it's okay. So for other viewers who will watch the recording, they also what they may do is they may pause the video right here and try the solution themselves, and then play it after they have say found a solution and compare the results. Okay. So sorry again for the inconvenience to the current viewers who are in the class today. I am showing the solution right now just for saving time because we already passed 2 hours. So I hope that's okay. Okay, it's actually a very good question. So the question is that this is the schematic representation of the process, that is there is a cycle operating between a source and a sink. Okay, so in this case the system is at a temperature of 200 Kelvin. Okay, and let me go to the question again. Okay, the system is at 200 Kelvin and the thermal reservoir is at a temperature of 100 Kelvin. So what is the maximum amount of work that can be obtained when the system is cooled from this 200 Kelvin to 100 Kelvin? Okay, so basically it is stating that to get some work we need to use a heat engine between this system and the reservoir. Okay, that's the key thing to consider, because there is no way or that if we just keep this system in the reservoir, if we just touch this system in the surrounding, if you just touch or keep in contact this system in the reservoir, that they will produce any kind of work. Okay, for the work to be achieved, we need to use a heat engine that operates between this system and the reservoir and produces some kind of work. Okay, I hope this concept is clear. So that's the first thing that you need to grasp. Okay, to produce work at a temperature difference, we need to use a heat engine, a direct heat engine. Okay, so this is a schematic representation of that thing. So consider that the system rejects a heat Q1 when it is kept in contact with the reservoir. When it is being cooled from 200 Kelvin to 100 Kelvin, it rejects heat Q1 and produces a work W. And since from the first law we know that for a cyclic process, Q1 plus Q2 would be equal to W, or Q2 would be sorry, Q1 minus Q2 would be equal to W, or Q2 would be equal to Q1 minus W. Okay, so from first law we can say that the heat rejected from the heat engine would be Q1 minus W, okay, for a cyclic process. Now the heat removed from the system, that is Q1, would be given by integral of Cv dt from T1 to T2. Okay, since we are given Cv in the question, this is equal to AT square, we have to use Cv for this particular case. Then AT square, where A is 0.042 integrated, where T square has to be integrated from T1 to T2. Now if we do the integration and put the limits, we will get 0.042 times T cube by 3. Limits would be T1 here would be your 200 Kelvin and T2 would be 100 Kelvin, because T2 is your final temperature. So limits are from 200 to 100. If you do that, you will get Q1 to be equal to 98 kilojoules. Okay. Now the net change the entropy of the system, that is net change the entropy of the system, would be Cv dt by T. Okay, since it's a constant volume process that we need to consider, then the second part, again, just I think it's just better if I write it. We have TdS is equal to du plus pdv, or ds is equal to du by t plus p by t dv, or ds is Cv dt by t plus pv is equal to rt. So p by t would be equal to r by v plus r by v times dv. Okay, or S2 minus S1 would be Cv ln T2 by T1 plus R ln B2 by B1. Okay, so let me just go back. Okay, sorry, I think this should have been plus. That's why this should have been plus. Okay, sorry for going there back, but it will be shared in the class. I don't want to remove to have any kind of confusion to the other students or the viewers as well. So since it is a constant volume process, so this one, this term would be equal to 0. Okay, so we will be left with this part. So since delta S system would be Cv dt by t integrated from T1 to T2. Since Cv is not constant, as in this case, that's why we cannot obtain this step directly. Okay, we have to start from this step. So we will have integration from T1 to T2, Cv dt by t. Now Cv is your AT square, or 0.042 t square dt by t. Now 0.042 can be taken out of the integration. We will be left with t square by t, or t dt. If you integrate t dt, we will get t square by 2. Integrated from T1 to T2, again T1 is 200, T2 is 100, where 100 is the T2 is the final temperature, this is 100. So if you do that, you will get delta S system would be equal to minus 630 joule per Kelvin. Okay. Now the change in the entropy of the reservoir, that is this one, would be the net heat interaction divided by temperature of reservoir, because reservoir is at a constant temperature. Okay, this is the definition of thermal energy reservoirs, that the reservoirs are essentially at constant temperatures. So the net heat input to the reservoir would be 98 kilojoules minus the net work obtained from the heat engine, that is as shown here, divided by 100 Kelvin. Okay, so it would be 98,000 joules. 98 kilojoules can count into joules minus W divided by 100 joule per Kelvin. Okay, and delta S of the working fluid, it will be 0. Why? Because since it operates in a cycle, we know that the net change in the entropy for a cyclic process would be 0 in a reversible case. So delta S working fluid will be equal to 0. So now the entropy change of the universe, that would be equal to delta S universe will be equal to delta S system plus delta S universe. So delta S system, if you go back, was equal to minus 630 joule per Kelvin. Okay, so it is minus 630 plus 98,000 minus W by 100. So that's why we converted this heat interaction to joules from kilojoules. Okay, so since we know that this delta S universe always has to be greater than or equal to 0. So it would imply that minus 630 plus 98,000 minus W by 100 should be greater than or equal to 0. Or if you divide all the terms by 100, or you just simplify this term, you will get 980 minus W by 100 minus 630 to be greater than or equal to 0. Or W by 100 is greater than or less than equal to 350. Or work done is less than or equal to 35,000 joules, or work done is less than or equal to 35 kilojoules. So keeping in mind the principle of entropy, and then we get that the maximum possible work that can be obtained from this cycle, considering all the processes to be reversible from the principle of entropy, we'll get that the maximum possible work that we obtain is 35 kilojoules. Okay. So yeah, so that's all for today from my end, and if there's any doubt, you can ask in the, since today time is over, so maybe you can put that doubt if there is any in the discussion forum, or else that's all for today from my end, and thank you. I hope the solution was clear. If there is doubt in this particular solution, you may ask, but if there's not, then I think it's we can just end the class today. Thank you so much.